Here I am adding my folder path and building the vector index. Now let's search for people at restaurant and eating food. Now we got few images that are similar to the query. Now we can check with few other queries. In this project, we are going to build a multimodal image search application using Python, OpenCLIP, FAISS and Streamlit. The application supports two types of search. The first is text-to-image search. For example, you can type queries like red car, images with white shirt, or mountain landscape, and the system will retrieve the most relevant images from the dataset. The second is image-to-image search. Instead of typing a query, you simply upload an image and the application finds visually similar images. Now let's understand how the system works behind the scenes. The architecture consists of two main stages, indexing and searching. Let's start with the indexing stage. First, the user provides a folder containing images. The application scans all the images, including those inside subfolders. Next, each image is processed by the OpenCLIP image encoder. OpenCLIP converts every image into a numerical vector called embedding. So instead of storing pixels, we are storing the semantic information contained in the image. Once these embeddings are generated, they are stored inside a FAISS vector index. At the same time, we save the corresponding image path. This allows us to map search results back to the original images later. After the indexing process is complete, the system is ready for searching. Now there are two ways users can search. The first option is text search. When a user enters a text query, OpenCLIP converts that text into embedding. Here OpenCLIP maps both images and text into the same vector space. This means a text embedding can be directly compared with the image embeddings. FAISS then performs a similarity search and returns the most relevant images along with the similarity scores. The second option is image search. In this case, the user uploads an image. The uploaded image is passed through the same OpenCLIP model, which generates an image embedding. That embedding is then compared against all indexed image embeddings stored in FAISS. Finally, the system retrieves the most visually similar images and displays them to the user. The major libraries that we use for this application is OpenCLIP and FAISS. OpenCLIP is the core model that generates embeddings for both images and text. As a result, we can perform both text-to-image and image-to-image search using the same model. Next, we will use FAISS, a vector search library developed by Meta. FAISS stores the embeddings and performs fast similarity search. This allows us to efficiently search through thousands of images in just milliseconds. Finally, we will use Streamlit to build the user interface. Streamlit allows us to create an interactive web application with minimal code. Using Streamlit, users can easily enter text queries, upload images, and view search results directly from their browser. Let's dive into the major methods used in this application. We will start with the most important one, that is build index. This function is responsible for creating the vector database that powers our image search system. So what happens when we run this function? First, it scans the dataset folder, including all the subfolders, and collects every supported image. Once the images are found, each image is passed through OpenCLIP. OpenCLIP converts an image into a numerical vector called an embedding. For example, this image will be converted to an embedding like this. So instead of storing the image as pixels, we are now representing it as a vector that captures its meaning. But before storing these embeddings, there is one important step: normalization. We normalize them. So why do we do this? Different embeddings can have different length. Normalization makes all embeddings have the same length. So similarity comparisons become much more reliable. In OpenCLIP, image embeddings are normalized. Also, text embeddings are normalized. This allows us to compare them fairly using cosine similarity. Next, we store the image path. This may seem simple, but it's very important. Because later, when FAISS returns a matching result, we need a way to map that result back to the original image. Before storing the embeddings in FAISS, we convert them into NumPy array. Now we are ready to create the FAISS index. Think of this as creating a searchable vector database. If your dataset contains thousands of images, you will end up with 1000 embeddings stored inside FAISS. Next, we add the embeddings. And finally, we save the index. This creates the file called FAISS_index.bin, which contains all the image embeddings. We also save the image path. This creates image_paths.pkl, which stores mappings like this. So after running build index function, we will get two important files, FAISS_index.bin, imagepath.pkl. At this point, our image database is ready. Now let's move to the application startup section. Before loading the model, we first check whether a GPU is available. If an NVIDIA GPU is detected, the application uses CUDA for faster processing. Otherwise, it falls back to the CPU. Next, we load the OpenCLIP model. This loads both the OpenCLIP model and the pre-processing pipeline. Here, VIT-B32 is the vision transformer architecture used by OpenCLIP. This model offers a great balance between search quality, inference speed, and hardware requirements. If you have a more powerful GPU, you can experiment with larger models for even better retrieval performance. Next, we move the model to the selected device. This sends the model to either the GPU or the CPU. Now that everything is loaded, let's see how the searching actually works. First, we will look at search by text. This function enables text-to-image search. A user enters a text query, OpenCLIP converts it into an embedding. FAISS searches the vector database, and the most relevant images are returned. The first step is tokenization. Suppose the user enters red sports car. The tokenizer converts that text into a format that OpenCLIP can understand. Next, we generate the text embedding, which produces something like this. Now comes the search step. FAISS compares the query embedding against every image embedding in the database. When we get the result, we apply a threshold. So only strong matches are returned. Finally, we use the returned IDs to retrieve the original image path and display the result. Now let's look at search by image. This function performs image-to-image search. Instead of typing text, the user uploads an image. The first step is pre-processing. Here, the image is converted to RGB, resized and normalized, converted into a tensor, and sent to the selected device. Next, we generate an image embedding. Just like before, we now have a vector representation of the uploaded image. FAISS then compares this embedding against all stored image embeddings. The highest scores represent the most visually similar images. And from this point onward, the workflow is exactly the same as text search. We retrieve the image path, load the corresponding images, and display the result to the user. And that's how both text-to-image search and image-to-image search work using OpenCLIP and FAISS. Now let's talk about the hardware requirements. The project can run perfectly fine on a normal CPU. However, if you have an NVIDIA GPU, embedding generation and indexing will be significantly faster. This becomes especially useful when you are working with large image datasets. Now let's set up the application. First, clone the repository. You will find the repository link in the description below. Next, create and activate a Python virtual environment. Then install all the required dependencies using this command. Once the installation is complete, we are ready to launch the application. Now run this command to run the Streamlit application. After a few seconds, the Streamlit application will start and you can access it directly from the browser. In this UI, we can give the path of the image folder that we want to search. Here, we need to build vector indexing for those images. I have some images in my folder to test. Here I am adding my folder path and building the vector index. Based on the number of images that you have, it may take time to build the vector index. Once we are done with the vector index, now we can search the images. So here I am trying to search for some images that have waterfall. So here I am typing tour and waterfall. Here you can see the result. So the first images are the top ranked images based on the vector similarities. It should match with the keywords tour, waterfall, etc. Here you can see the file name, score and the path of the image as well. Now let's search for people at restaurant and eating food. Now we got few images that are similar to the query. Imagine you have hundreds or even thousands of images stored on your computer and one day you need your passport size photo. You know it's somewhere inside a particular folder, but you don't remember the file name or exactly where you saved it. So instead of manually opening folders and scrolling through countless images, let's use our application and simply type passport size photo and click search. And there it is. Now we can check with few other queries. It also supports image to image search. So let's upload an image. As you can see, the application returns images that closely match the uploaded image. Imagine you have thousands of images stored on your computer. Over time, it becomes difficult to remember file names or folder locations. With this application, you simply describe what you are looking for and it will find the results. So with the application, we can search using either text or another image. And that's what makes multimodal search so powerful. I will share the complete project code link in the description box. So feel free to check it out and try the project yourself. While this project works well as a multimodal image search engine, there are several improvements we can make to enhance its capabilities. The first improvement is automatic folder monitoring. Currently, whenever new images are added, we need to rebuild the index manually. Instead, we can monitor the folder and automatically dictate newly added images. The second improvement is incremental indexing. Right now, the application regenerates embeddings for all images whenever the index is rebuilt. A more efficient approach would be to generate embeddings only for newly added images and append them to the existing vector index. The third improvement is metadata-based search. Along with embeddings, we can store additional information such as file names, folder names, file sizes, and creation dates. This allows us to apply filters and provide more meaningful search results. So these are few points that we can add to improve the result. So that's all for today's video. If you found this project useful, please consider to support the channel. Thank you for watching and see you in the next video.